The history of aeroballistics at Sandia National Labs began in the 1940s with a vision and a passion that would eventually become a world-renowned aerospace capability for the United States of America. Aeroballistics is the science of aerodynamics and flight mechanics, dealing with the motion, behavior, and effects of projectiles, especially bullets, aerial bombs, rockets, or similar objects, and includes the 6th degree of freedom motion of various vehicles. But the field of aeroballistics and its history will be forever intertwined in the broader context of all things aero. Sandia's origins in aeroballistics started in 1945 with the testing of the first atomic bomb shapes of Little Boy and Fat Man. Eventually, these atomic weapons were detonated over Hiroshima and Nagasaki, Japan, which led to the end of World War II. Historically, these weapon shapes also have the distinction of being aerodynamically incorrect, and it's said that they were probably designed by a nuclear physicist and not an aerodynamicist. The defining elements of the 1940s and the 1950s in the aerospace industry set the stage for an all-out international space race and helped position Sandia to attract innovative professionals, develop a broad range of technologies, and create a unique set of capabilities. In 1941, Germany launched the first man-made object, the V-2 rocket, into space. In 1947, American test pilot Chuck Yeager broke the sound barrier in the rocket-powered Bell X-1. And in 1957, the Soviet Union launched the first artificial Earth satellite and the first dog into space with Sputnik 1 and Sputnik 2.
1957, year of space and Sputnik dogs. Laika, first space traveler, was ready for the takeoff. A shocked America attempted to launch a grapefruit-sized satellite on the Vanguard rocket with disastrous results.
The world was very nervous. Of course, the Russians had suddenly been found to have the bomb, and we thought we had a lead, and we suddenly didn't know that we did.
Sputnik was about then. NASA was formed a few years later. Let's see. A lot of things were going on then.
Well, the Cold War was in full swing. We were in a competition with the Soviet Union to see who technologically could have the superior military systems. So again, Sandia was brought in on a number of different occasions to help bolster what the Department of Defense was doing to help counter the Russian threat.
During that era, Sandia was designing, developing, and testing the non-nuclear components of nuclear weapons in the stockpile.
When a bomb's released, it has to fly, you might say, straight and true. And so the aero group had the responsibility of putting fins and spoiler bands or whatever so that they would have a repeatable trajectory.
Harold Vaughn pioneered flight dynamics work at Sandia for all the lab's nuclear ordnance. He laid the basic analytical foundation for the aeroballistics of bombs, nuclear shells, reentry vehicles, guided missiles, and rocket systems.
I worked with Hal Vaughn a lot. Very sharp person. Very, very impressive.
Harold Vaughn, he's the guy who could do anything.
Another pioneer, Randy Maydew, was tasked with examining the feasibility of developing tactical, externally carried nuclear weapons from low altitudes using transonic parachutes.
We did a lot of wind tunnel testing with different shapes at that time, configurations. And we did test at the wind tunnel establishments that were on the east. The Ornament Engineering Development Center. It's probably one of the biggest wind tunnel complexes there is.
Well, when they started testing, they would test on to some point where they could work day and night.
At that time, the labs didn't even have a parachute capability. But that soon changed when the low-level delivery parachute program was started in 1954. Sandia designed a parachute test vehicle with a spike nose, equipped it with Pluto cameras developed by Ben Benjamin to photograph the parachute opening phenomena, and tested it in various locations and proved that a parachute could open reliably at speeds up to Mach 1 from very low altitudes. Randy Maydew worked closely with David Clausen, who initiated the lay-down weapon program, and out of that work came the B-43, the first of many lay-down bombs. Sandia conducted classified wind tunnel tests at all the major facilities across the country. Wind tunnels were being used extensively to measure the aerodynamic characteristics of bomb shapes and to simulate the release and separation of a bomb from an aircraft. The demand was so high that some of the wind tunnel facilities ran 24 hours a day, 7 days a week. It became apparent that Sandia needed to conduct their own tests, so in 1956, the labs built what they called backyard facilities, starting with a 12-inch transonic wind tunnel. Harold Spar spent about 15 years developing and modifying computer codes with Nielsen Engineering in California, and he successfully pioneered the use of release and separation codes to accurately predict how a bomb separates from an aircraft. Sandia also developed a rocket-boosted guided bomb for a standoff weapon system called Tiger, which when released over a target would circle like a boomerang and return and impact at the same target location. The basic design requirements for aerodynamic characteristics of bombs hasn't changed much over the years. In all, 34 ballistic nuclear bomb weapon shapes weighing as much as 42,000 pounds have been studied and/or tested since 1943.
Well, as some of the different projects developed, different expertise had to be brought in.
Thing I think I liked about working in Randy Maydew's aerodynamics department was it was like a big family.
It's just a bunch of interesting people.
The people we had in the group were just outstanding.
A lot of people don't know this, but we launched a lot of rockets in our time. Most of those rocket launches supported the nuclear weapon program, but at one time we were second to NASA in terms of the number of rockets that we flew.
The rocket program originated in the Aero department in 1957, and the first rocket system developed by Sandia was the Mach 5 TV.
Where I was involved with the Aeroballistics was involved with sounding rockets and devices like that that we used when they were doing nuclear testing in the atmosphere. We shot a lot of rockets that would go up and fly through the debris cloud and take measurements of what was in the cloud, and by doing so you could determine the amount of yield and just how everything worked.
The next rocket system, Doorknob, was developed to carry diagnostic instrumentation and to gather radiochemical samples for Operation Hardtack at Johnson Atoll in the Pacific Ocean in 1958.
In the early days of the United States doing atmospheric nuclear testing above the Earth's atmosphere in space, these tests were conducted in the South Pacific. So they would put a nuclear test device on the head of a rocket system and launch the rocket up, clearing the atmosphere, and the nuclear device would then detonate. And so they would launch the nuclear device from Johnston Island, and simultaneously they would launch a dozen or more rockets from Kauai that carried instrumentation on board. Time to arrive in their altitude at the same time that the test device detonated.
The first one I remember was Operation Dominic in '62. And that's when I first got into, you might say, the rocket business.
The Nike Apache system was then developed to launch recoverable payloads for weapon diagnostics, nuclear debris sampling, and meteorological data for the fishbowl high-altitude tests of the Dominic Test Series in 1962.
And as it turned out, they used Thor missiles, and the Thors wouldn't fly right. And in June, they tried the second one, and the rocket on the pad started leaking liquid fuel, caught on fire with a live nuke in the front end. The Air Force had a destruct system on the missile. When that failed, they called the Sandia bunker, and Morgan Cram and some of his troops were in there with a separate ability to safe that warhead. That means they blew it up. So it scattered special nuclear material around the island.
So most of the people in aeroballistics were working on the Stripey rocket.
Sandia developed the Stripey in just 2 months to replace the Thor boosters, which were failing during launch at Johnston Atoll.
And 9 weeks from the time they turned on the laboratory till they launched the first Stripey with no payload on it, and that worked pretty good. So they launched 2 more with water payload, and they worked pretty good too.
After the Nuclear Test Ban Treaty went into effect in the fall of 1962, Sandia continued to develop and launch rocket-boosted warhead carriers and sounding rockets in support of the nuclear readiness posture.
I was one of the first guys that came in to the rocket group after Dominic. I got there in '62. And so for many, many years they called me the kid. I was young. I was young. I see. When I got to work at Sandia, I thought I was 27 years old, but these other guys had been there working from essentially the beginning. They were involved in Bikini, they were involved in we talk about people that were forerunners of all that. Come to mind, Glenn Fowler, and he was our director of field tests when I went to work in there.
The 1960s and the 1970s witnessed a continued space exploration, first out of our atmosphere and past other planets, then walking on the moon and landing on Mars.
This is very much a testing culture, and that's at the heart of the origins of this community, long before we mastered the computers that we have today. The only way to gather data and to understand phenomena associated with flight testing was to actually build articles and test them.
It was a philosophy that Don held that any vehicle that you put up or there, any test vehicle, actually went through the full environments.
We tested everything on the ground, since Sandia had a huge test capability. And that way we broke them on the ground and fixed them before flight test. Where in the case of most of industry, they had a flight vehicle and what they call the hangar queen. And they'd run the hangar queen through all the testing and treat the flight vehicle with essentially white gloves. And when it came time to fly it, always something went wrong with the actual vehicle.
Sandia doesn't have too many failures. Don Regali, my former boss, used to keep a chart on his wall that would show the success rating of all the flights that Don had done, some 80 or so shots, with a success rate in the high 90s.
And the labs continued to conduct joint scientific experiments with NASA and the Department of Defense, as well as other countries.
Sandia has utilized most every flight test range that there has ever been in this country. We've been to all of them.
Hawaii for sure, Alaska, White Sands, Wallops Island in Virginia, Cape Canaveral or Cape Kennedy.
I like Tonopah better than I did Kauai because Tonopah was a little more rugged terrain. I had one coworker that called it the moon with air.
I got to go out before the flight for a meeting at Kwajalein, and that was pretty spectacular out in the middle of the South Pacific.
We would launch scientific payloads to examine the aurora borealis. And there we were interested in learning about the Earth's magnetic field. We did experiments off the east coast of Africa.
There was a couple eclipse tests. One we set up our own range in a place called Lancelin, Australia, Western Australia. And then we shot a couple vehicles off a oil platform off the coast of Kenya.
We once went to Australia for a solar eclipse. We fired 2 rockets. Well, one of them, the gyro failed and it didn't point right. And the other rocket, it pointed right. We got good data. We knew we had good data. And then the recovery system failed and it sank to the bottom of the Indian Ocean.
One scientific experiment involved launching cosmic particle research rockets from Kauai to examine black holes in the universe, record stellar X-ray emissions from distant constellations, examine zero-G effects on liquid helium, and inject an ionized barium cloud into the Earth's own magnetosphere.
We started a program on rain erosion, we called it, to try to fly missiles up through actual clouds and make measurements of what happened to the nose tip or the heat shield. Later on, we went to a 3-stage system with a tater, or tailless terrier recruit, and we got up to over 10,000 feet per second with that, flying up through storms.
It was designed primarily by Bob Fellerhoff and Larry Ralston.
We had to have a very robust recovery system. We had some excellent designers in the way of parachutes and recovery. And so the way you pick these payloads up, there was a flotation bag that actually floated the system on the water. The parachute and the payload were submerged. By the next morning, a Russian trawler moved in on that payload. These payloads were classified. We got back out there and picked up the payload before they could get it. But that was an exciting time to actually be there, to be in the helicopter, to get our payload back in the face of an adversary that wanted it. There's lots of stories.
And in 1964, Sandia entered into reentry vehicle aerodynamics design and testing, from intermediate range ballistic missile, or IRBM, and intercontinental ballistic missile, or ICBM trajectories at velocities as high as 24,000 feet per second. And while the Aero department was busy working on RVs and all its other initiatives, some of its staff would soon be called upon to help out in a very different capacity on another continent. On January 17, 1966, a KC-135 collided with a B-52 during a refueling operation off the coast of Spain. 4 B-28 thermonuclear weapons were being carried in the bomb bay of the B-52. 3 of these B-28s landed within a mile of the coast and were immediately located, but 1 of the B-28s was missing. Randy Maydew and then Bill Barton arrived in Palomares, along with 4,000 other civilian and military personnel and 18 Navy ships. An interview with a local fisherman who witnessed the crash aided in the recovery of the missing bomb, which was found 80 days later in the sea. Then, from 1967 to 1968, the lab studied 6-inch and 8-inch nuclear artillery shells.
So the challenge was to build a nuclear round that had the same flight characteristics as a conventional projectile.
When you stand back and look at it, it's probably not a very good idea, because the land that you've supposedly fired into, you don't want to occupy now. You know, it's radioactive.
Well, I had good people working for me, and that helped a lot, so we just sort of worked as a team.
Well, Vietnam certainly was happening.
Sandia had developed these darts in the 1970s, in the Vietnam era. And so they're used to put sensors in the back end, to fly them ahead of troops, to send them places that they couldn't get to in the jungle, and they would just listen for what's going on around them. And a fellow by the name of Eric Reese was here at Sandia way back when. He said he met some Army guys, and they talked about these DART vehicles saving their lives.
I hired in about the 1980s, so the big challenge during that time frame was making our own reentry systems functional and robust. They were having problems with heat shield design, nose tip recession, and the robustness of the vehicles was not well up to par.
RVs are subjected to brutal conditions as they re-enter the Earth's atmosphere at extremely high speeds. The temperatures a nose tip is exposed to at a 50,000-foot altitude and a velocity of 21,000 feet per second can reach 5,000 degrees Fahrenheit. Sam McAlay's group analyzed RV heat shields from an aerothermal perspective based on a series of trajectory, flow field, aero heating, ablation, and materials property codes.
Sandia was one of the early developers of advanced materials, not only the phenolics such as carbon phenolic and silica phenolic, but also understanding advanced materials such as carbon-carbon heat shields.
Over time, control, guidance, and navigation technologies were created, which ultimately enabled very sophisticated missions and the development of rocket systems that were much larger, vertically launched, and actively guided in all phases of flight. In the 1980s, improved computational fluid dynamics was used to calculate the aerodynamics flow field on flight vehicles, particularly the flow field over maneuvering re-entry vehicles traveling at speeds up to Mach 25. This revolutionary technology used computers to develop aerodynamic models and enabled aerodynamicists to design complex vehicles that could fly at hypersonic speeds.
In many cases, Sandia was 20 to 30 years ahead of its time in these advanced technologies.
The defining project for me that happened while I was a member of this community was a program we call SWERVE. And SWERVE is an acronym, gotta love the name, for Sandia Winged Energetic Reentry Vehicle Experiment. You put all that together, you get the word SWERVE.
SWERVE was a very challenging project done in the mid-1970s and 1980s.
SWERVE was, for its time, one of the most amazing aerodynamic design challenges that America faced in that period of time. But it was all done under the cloak of secrecy. It was highly classified at the time. Elements of it still are.
They used our reentry system technology to not just fly ballistic systems, in other words, point and shoot, but maneuvering systems that could fly to a designated spot like an aircraft.
Basically, SWERVE was a maneuvering reentry vehicle that was designed to fly Mach 14, Mach 15, about 15 times the speed of sound for very long distances.
SWERVE has undergone more wind tunnel tests than any other U.S. flight vehicle other than the Space Shuttle. And it was manufactured with an ablative cooling material that eliminates heat by vaporizing part of the vehicle's surface. The 1980s and the 1990s were turbulent times as President Ronald Reagan started the Strategic Defense Initiative, nicknamed Star Wars, to develop a sophisticated anti-ballistic missile system to prevent attacks from other countries, specifically the Soviet Union, which increased Cold War tensions rather than decreasing them. Don Regali was building a robust rocket program for the defense of the nation. He was creating an outstanding reputation for Sandia with a series of successful Department of Defense systems and launches in a highly advanced work for others program area.
I feel like I stepped into that community sort of at the end of the second act, I guess. If you can imagine that the community that I joined in '81 when I came back had been in existence going all the way back to the 1950s.
So when I started, it was a huge department or a huge center, if you will, of aerodynamic experts and flight mechanics experts.
In 1985, Sandia started developing a launch vehicle for anti-ballistic missile targets.
As the targets program progressed, we would have, 4 to sometimes as many as 7 projects going at one time trying to support the Ballistic Missile Defense Organization. So it was what we call fly nights, work days sometimes. It was very active.
The first Stars 1 launch of an actual target occurred in 1993. The highly publicized and extremely controversial Star Wars initiative may have led the Soviets to believe that Reagan would spend more money on weapons than they ever could, and it might have helped end the Cold War. After the Berlin Wall was torn down in 1989 and the Soviet Union was dissolved in 1991, the Department of Energy's National Labs began to build and launch targets as part of the United States Ballistic Missile Defense System. Exo-atmospheric kill vehicles were deployed to seek out and destroy these targets kinetically, or, in other words, just through the force of the collision and not through any type of high explosives.
Hit a bullet with a bullet, as they called it. It was hit to kill.
Sandia successfully built and launched dozens of these kinetic energy interceptor targets and supported a series of integrated flight tests, or IFTs, supporting what became the National Missile Defense Element ground-based interceptor of today's operational ballistic missile defense system. The turn of the century brought with it first fears that all the computer systems would fail, and then one of the worst terrorist attacks on the United States in recent history, on the World Trade Center and the Pentagon on September 11, 2001. It prompted an all-out war on terrorism. It also led to the creation of the Prompt Global Strike Program to provide an alternative to the use of nuclear weapons in a crisis situation. Then the Tactical Missile System Penetrator, or TACMS-P, was developed in 2001. Lockheed Martin partnered with Sandia National Labs to integrate a live Earth-penetrating warhead with a modified Army TACMS missile. It was fired from an existing Army launch system and successfully impacted a fixed hard target. We flew 8 STARS missions in support of missile defense system development. The Stars 1 rockets have been used successfully as target launch vehicles in all the tests of the ground-based interceptor missile through 2008. This was just the beginning of an extensive rocket program that's still in existence today. To date, Sandia has launched over 1,500 missions on 60 different types of booster systems from 19 launch sites around the world. And the labs, who always seem to be on the edge of technological advances, developed and launched the U.S. Army's Advanced Hypersonic Weapon, or AHW, in 2011. And this was an historic flight. It was the first time 8 grid fins were used to stabilize a U.S. ballistic missile system. It was the first time a Sandia-developed booster had flown from a low-altitude, long-range horizontal flight path at the edge of the Earth's atmosphere. And it was the first time a glide vehicle flew at hypersonic speeds at that altitude and with that range.
The future is wide open for Sandia. While aeroballistics has been a wonderful technology area, we're sort of taking that to the next level, looking at maneuvering systems, looking at new ways, new concepts of flying flight systems that we've never thought of before.
I bet I've had the best career anyone could have.
Well, if I wasn't 80 years old, I'd like to go back and do it again.
The history of aeroballistics and all things aero at Sandia began with a mission and a vision from some very extraordinary individuals who accomplished some incredibly amazing feats and made critical contributions to some of the largest programs ever undertaken by Sandia National Labs.
I have a launch. Interceptor away.